Low-carbohydrate diets are praised for forcing the body to burn fat, creating alternative fuels like ketones for the brain to use instead of glucose. However, this narrow focus on the brain overlooks what happens to the mitochondria and the rest of the body's working organs when carbohydrates are restricted. The nervous system has extremely high energy demands, but is notoriously sensitive to damage. As a result, it cannot safely use fat as a direct fuel source, relying instead on a steady supply of glucose or ketones. While the brain is fueled by these alternative sources, the heart, liver, kidneys, and muscles are left to bear the burden of systemic fat oxidation to keep the system running. Forcing the body's most active tissues to run on a fuel that the brain itself cannot utilize raises questions about the overall efficiency of burning fat. To understand the difference, we have to look inside the mitochondria of a working muscle cell and compare how it processes fat versus glucose. Saturated fats, such as palmitate, deliver electrons to the energy-producing machinery in a way that differs significantly from glucose. Glucose provides easily managed electron carriers, called NADH, while fat relies on a cumbersome carrier, FADH2. This forces electrons into the transport chain too rapidly, causing them to pile up. This backup is caused by intense physical competition at the electron transfer flavoprotein, or ETF. Metabolizing fat does more than just swap one fuel for another. It creates a mechanical bottleneck that overwhelms the mitochondrial machinery. When electrons become trapped at this bottleneck, they begin to spill out of the transport chain at multiple failure points. These escaped electrons erupt from complex 1, complex 3, and the ETF, transforming into volatile molecules known as reactive oxygen species, or ROS. These species, including superoxide and hydrogen peroxide, bounce through the cell, causing oxidative damage and degrading the surrounding cellular structures. This is a consistent biological observation. Research shows this exact increase in oxidative stress when burning fat in pigeon hearts, cow liver cells, and human muscle alike. In response to this damage, the cell triggers an emergency defense mechanism known as uncoupling. Uncoupling opens a vent in the mitochondria to dissipate the built-up cellular gradient, which halts the production of these damaging reactive oxygen species. However, this vent comes with a steep cost. By stopping the production of ROS, the cell also stops the production of essential ATP energy. When forced to rely on fat, the cell faces a choice: endure continuous oxidative damage or shut down its own energy production to survive. Moving from the microscopic cellular level back to the scale of the entire human body reveals the broader impact of this metabolic state. Systemic fat oxidation is a less efficient state than the one provided by carbohydrates. While alternative fuels sustain the brain, the rest of the body's vital organs are subjected to continuous oxidative stress and mitochondrial dysfunction. This persistent stress forces tissues to continuously trigger their emergency events, which lowers the overall energy yield of the entire body. If the goal is highly efficient energy production with minimal cellular stress, the biological evidence points towards carbohydrates rather than fat as the primary fuel.